Hello and welcome to this video walkthrough for the OCR Gateway Science Physics Paper 1 from June 2015. We're focusing on this video in section C, which is actually covering the topics in P3. It is worth reminding you about the equations on page 2, and this particular topic, P3, has most of the equations, but they are all in that first column. So these are all the equations that you'll need for P3. And it's just useful being aware of where these are. And I want to point out this equation in particular one, because that seems to be the equation that most students forget about, basically. And in fact, this equation is exactly the same as this equation, but it's just in symbol form. And it's also worth pointing out that the S here does not stand for speed, it stands for displacement, okay, which is a vector form of distance. So in other words, if you want to work out how fast something is traveling, then you can use this equation if that object is accelerating. Question 9. This question is about speed. So pupils at a school measure the time cars take to travel 2 100-meter lengths. Okay, let's just change the colour of that. Okay, so look at the diagram. So you have 2 lengths, A, B, C. Each length is 100 meters. Look at the results that they collected for 4 cars passing the school. So here we have the types of car. We've got a Golf, a Fiat, a Jaguar and a Skoda. We have the time taken to travel length 1 in seconds. So we've got 9, 8, 8 and 7 seconds, and then the time taken to travel length 2 in seconds, 8, 8, 8, 7. So we got some times in seconds, so the faster the time, the quicker the car was travelling. So scrolling down to find out what we've got to do. Which car's speed is increasing as it travels from A to C? Well, what we're looking for is a change in the time, so we're looking for the time to get shorter. So here we have our Golf. It takes 9 seconds to travel the first 100 meters and then 8 seconds, which is faster. So therefore, this is the car that is accelerating. So our answer for this question is Golf. The speed limit on the road is, in front of the school, is 13 meters per second. Calculate the time it takes for a car travelling at a speed of 13 meters per second to travel 100 meters. So use your answer to explain if any of the cars are travelling faster than the speed limit. So if any of the cars are actually breaking the speed limit. Naughty cars. Okay, so obviously the equation that we're going to use is speed equals distance over time. Okay, so we need to change the subject and make t the subject. So t becomes the distance divided by speed, which is obviously 100 meters divided by 13 meters per second, which leads us to 7.7 seconds. So what that means is anything that's taking less time than 7.7 seconds is going faster than the speed limit. So our Skoda, naughty Skoda, is actually the one that's breaking the speed limit. So part B, look at the information about thinking distance and braking distance for cars travelling at 13 meters per second. So we have 4 drivers, Sam, Chris, Joe and Ben. We have the thinking distances in meters and their braking distance in meters as well. And I can see from this first column that Joe stands out a little bit. Her thinking distance seems to be a lot longer than the others. And from the second column, I can see that Chris's braking distance seems to be a lot bigger. So I'm looking for things that stand out. One of the drivers is tired after driving for several hours. Suggest which driver is tired. So I'm looking for, so if you're tired, your reflexes are going to slow down. So if your reflexes are going to slow down, then your thinking distance is going to increase. So the answer is Joe, and our explanation is very straightforward. Joe has the longest thinking distance. Then moving on, one of the drivers was driving on an icy road. Suggest which driver was doing that. So that's clearly Chris, because he has the biggest braking distance, and that forms the answer. Chris has the longest braking distance because there is less friction. So I've just mentioned because the roads are icy, there's less friction, which is why he's got the longer braking distance. And that's that question done and dusted. So moving on to part D. Sam's car uses a biofuel. She says that over time this does not increase the amount of carbon dioxide in the atmosphere. Is she correct? Explain your answer. Well, the important thing to realise about biofuels is that they're made from plants. Those plants normally have a good or very short regeneration time, so you can plant and grow them in very short amounts of time. So our answer is yes, she is correct, because plants take in carbon dioxide when they photosynthesize, which balances the carbon dioxide released when they are burned. So whilst you're growing these plants, they're taking in carbon dioxide from the atmosphere, and fine, you cut them down, produce biofuel and burn the biofuel, but that's just releasing the actual carbon dioxide that was taken in back into the atmosphere. So we say that this is carbon neutral because overall it's balanced, it's not upsetting the amounts of carbon dioxide in the atmosphere. Then B, some cars are fitted with ABS brakes to reduce injuries and save lives. Describe how ABS works and under what conditions it is used. So we just need to know what ABS brakes are. And a lot of you didn't know this when you did your mock. So ABS brakes are designed to go on and off automatically. So what they're doing is they're pumping the brake, so it is then less likely to skid in slippery conditions. So before ABS, when you were learning to drive, you were driving down the road, and if you hit an icy patch, then you were taught to actually manually pump your brake to try and reduce the skidding. And the ABS brakes just do that now automatically. Okay, question 10. Amy dives from the high diving board at a swimming pool. Look at the graph of her motion. So motion graphs are commonly an area where students do struggle. So there's two types of motion graph: distance time graphs, speed time graphs. This is a speed time graph, so you do have to recognize what the graph is telling you. And so I can see from this that we've got at time 0, Amy leaves the diving board, and obviously at this point P up here, she actually enters the water. So the first question says, calculate the height of the diving board above the water. Now there's two ways you can approach this. The first way is to realize that for a speed time graph, you can work out the distance traveled, in this case the height that she's dived, from the area underneath the graph. Okay, so if I just get this other color here, so if we work out the area of that triangle, then that will give us the distance. The other thing that you could do is you could just use the equation that's on paper 2, the equation that says distance S, so remember that's displacement, equals U plus V divided by 2 times the time. Okay, so again, remember, people forget that equation, but there's two ways that you could have thought this through. The key thing is you can't use speed equals distance over time because your speed is changing, it's increasing, and so that shows acceleration. If you did use speed equals distance over time, you would have got 1 mark. But to get 2 marks, you've got to do it this way. So what I did was I did the area under the graph. So the distance is equal to the area of triangle is half times the base times the height. So the base is, actually I've done the other way around. So the this is the height and this is the base. So the height is actually, if you look carefully in the graph and read across, it's actually 14, and here the actual base is 1.4. So we've got half times 1.4 times 14, which is 9.8 meters. If you use this exactly the same thing, you would have used U as being 0 because the starting speed was 0. You would have used the final velocity from this actual graph here, so that would have been V divided by 2 and then times it by T, which would have been 1.4. So you would have had to get these things from the graph, but you would have got the same result. Okay, so carrying on, B part 1. John thinks that he can find Amy's deceleration just after she enters the water by using points P and Q on the graph. Elaine thinks it's better to find Amy's deceleration just after she enters the water by using the gradient of the graph at point P. So remember, the gradient of a speed times graph is equal to the deceleration. But if you've got a curved line, the only way you can do it is by taking a tangent at a particular point, which gives you then the instantaneous deceleration. If the line is curved, which it is in this part of the graph, it shows that the deceleration is changing, and that's because as she goes through the water, she slows down because of the drag and resistance from the water. So explain why Elaine's method is better than John's to find the deceleration. So there's a couple of key points here. So the first thing we want to say is the instantaneous deceleration at P is more representative of when she enters the water, because she will be slowing down from that point onwards. And then the other point that we could say is because point Q is not actually on the line, we could say that's an anomalous point. So that's why Elaine's method would be better than John's. Last part of this question, part 2. Amy has a mass of 60 kilograms. Amy's deceleration as she enters the water is 20 meters per second. So we've got her mass there. We've got her deceleration here. Calculate the decelerating force on Amy just as she enters the water. So we have F equals ma, which is the equation from page 2. Mass is 60. Acceleration is 20. 60 times 20 is 1200. Lots of people wrote 120. So a bit of a silly mistake, unfortunately. And because it's only worth 1 mark, that silly mistake would have cost you on this particular question. All right, so question 11. This question is about kinetic and gravitational potential energy. It's a 6-mark question. It's a question that university people did pretty poorly on. And the main reason for that is because lots of people understood the changes between kinetic and gravitational potential energy in a roller coaster, but they didn't interpret the graph correctly. And they kind of just took the graph as looking like a roller coaster, so therefore that's what they were looking at. It's not true. You've got to understand what the graph is about. So it says, look at the graph. It shows how the speed of a roller coaster car changes with the distance travelled along part of the track. The roller coaster car starts from rest at the top of the track A. So this is the starting point down here. That's the top of the hill, because that's when the kinetic energy is 0, when the speed is 0, and when the gravitational potential energy is at the highest. And that was the thing that people didn't connect. They thought that this point was the top of the hill. Okay, so that's why people lost the marks, because they just didn't interpret the graph or translate the graph correctly. The roller coaster car starts from rest at the top of the track at A, okay, which is at the bottom here. The car and its passengers have a total mass of 400 kilograms. We'll need that for a bit later. So the point is this. The car is starting here, it's at the top of the hill. It's got 0 kinetic energy because it's barely moving, and it's got a lot of gravitational potential energy. Then it rolls down the hill and gains kinetic energy, so up to B. So up to B, the kinetic energy is increasing because this is speed, and so if the kinetic energy is increasing, the gravitational potential energy is decreasing. Okay, because that's the transfer process that's happening in roller coasters. And then at B, you've got maximum kinetic energy. This is the bottom of the hill here. And then it goes down up the other side. So it's going now up the actual hill, the second hill, to C. And so what we have is the kinetic energy is decreasing because the speed is decreasing. It's slowing down, slowing down, slowing down. And the reason why it's slowing down, slowing down, slowing down is because it's going up that second hill. And so the gravitational potential energy is increasing from B to C as the kinetic energy decreases. So that was the stumbling block. And the shame of it is, if people had just realised that, then a lot of you would have picked up your 6 marks here, or close to your 6 marks, because you understood the energy changes, you just didn't interpret the graph properly. So scrolling down to the answer, well, I suppose to the question and the answer, see if it fits. There we go. So we've got describe how the kinetic energy and the gravitational potential energy of the car changes in sections A, B and B, C of the journey, and calculate the difference in height of the roller coaster between A and B, assuming no energy is lost. That's what we like to do as physicists. We like to assume there's no friction or air resistance because it keeps things very simple. The acceleration due to gravity is 10 meters per second squared, and the quality of your written communication will be assessed in your answer. So let's keep it structured and logical and sensible with good scientific language. I've said kinetic energy increases from A to B and then decreases from B to C. This is obvious if you're looking at the graph and you're interpreting the graph. The speed is increasing from A to B, so therefore the kinetic energy must be, and the speed is decreasing from B to C, so therefore the kinetic energy, which depends on speed, is also decreasing. Then the second part of it is really straightforward. Once you've interpreted the kinetic energy correctly, obviously the gravitational potential energy just has the opposite effect. So when the kinetic energy is increasing between A and B, the gravitational potential energy decreases because it's going down the hill, and then increases from B to C. So this gets you a bulk of your kind of 2 or 3 marks because you've described correctly the energy changes. I've just said here, just to make it really clear, that the loss in gravitational potential energy is equal to the gain in kinetic energy, and vice versa, if we assume there's no energy losses. So if we ignore friction, then all the gravitational energy at the beginning is going to turn into kinetic energy, and then as the car goes up the other side of the hill, okay, so it's then going up the second hill, all the kinetic energy is going to turn into GPE, gravitational potential energy, if there's no energy being lost to the surroundings. Okay, so because of that, we know that if we can work out how much kinetic energy the car has at the bottom of that first hill when it's going at its fastest, then all of that energy must have come from the gravitational potential energy at the beginning. And of course we've got an equation for GPE which links to height, and what we've got to do now is we've got to calculate the difference in height of the actual roller coaster. So first part, let's calculate kinetic energy that the car has at the bottom of that first hill. We know how fast it's going from the graph. Okay, from the graph it's going at 16 meters per second. So its velocity is 16. Its mass from the question is 400, and obviously half is half, so it's half times 400 times 16 squared, and that comes to 512,000 joules. So then, thinking about the GPE, we know that 512,000 joules came from the energy that was stored because of the car's position at the top of the hill. None of it was lost, it's all gone into kinetic energy. So at the start, our energy was 512,000, and that was equal to the mass of the car times the acceleration due to gravity times the height above the actual track, height above the actual hill. So I've got this equation obviously from page 2. GPE is equal to mass times G times H. So I want to rearrange things to find out what H is. So H is going to be equal to 512,000 divided by 400 times 10, which is 4,000. And that gives me the hill height as being 12.8 meters. So I think the most difficult thing about this question was certainly interpreting that graph, but just look at the graph, check what the axes are telling you, and think how it relates to the question, which it was about kinetic energy and gravitational potential energy. Because it was a speed time graph, you should have realized that the graph was telling you what was happening to the speed, so it was telling you what was happening to the kinetic energy. So moving on to the last question, question 12, part A. Ben is considering buying a new car. He investigates how the cost of a journey changes with the speed of the car and the distance travelled. He does this for a car with a petrol engine and a car with a diesel engine. Both cars have the same size engine. Just to make it fair, look at the table for a petrol car. So here we've got a petrol car. We've got the speed. You've got a column where we've got speed in kilometers per hour, and then we've got this wide column here that is telling us the cost of fuel per kilometer for different distances. So we've got a 5 kilometer journey, 25 kilometer journey, and a 100 kilometer journey. So I can draw two conclusions immediately, not even looking at the diesel car, not even comparing to the diesel car. I can see two things very, very clearly. The first thing is that none of these numbers are changing as we increase the distance. So what that tells me is that distance has no effect of the cost of fuel per kilometer. Okay, and the other thing that I can see is then that as the speed increases and this pattern is followed for all of these, that as the speed increases, the cost of fuel per kilometer decreases until you get to this sweet spot, 80 kilometers per hour. And if you go above 80 kilometers per hour, then the cost of fuel per kilometer increases again. So there's two things that I've identified just from that table. I'm just going to scroll down now and see if that's true also for the diesel car. So let's have a little look. And so, yeah, exactly the same for the diesel car. Distance has no effect on the cost of fuel per kilometer, and it follows the same pattern that as the speed increases, you get to this sweet spot where it's most efficient and the cost of fuel per kilometer is lowest. But then if you go beyond that, if you try to beat your friends in a race or whatever, then of course that cost goes back up. So the third thing that I need to check then is, obviously we've got two tables, so I need to compare petrol to diesel. So what's the difference? Well, pretty obviously, if I'm just looking at these numbers, then diesel is cheaper, generally speaking, and that means the cost of fuel per kilometre for diesel is less than petrol, or say the other way around, the cost of fuel per kilometre for petrol is more than diesel. So what does the question ask us? So, what conclusions can Ben make about the cost of fuel per kilometre travelled using this data? Great. So those three things is worth 3 marks. Those three things we need to state. The cost per kilometre does not depend on distance travelled. The petrol engines cost more per kilometre than diesel engines. And of course, the third thing that I pointed out was the cost per kilometre decreases with speed up to 80 kilometers per hour, but then increases. So that's your 3 marks. Part B, battery powered cars cost much less to drive per kilometre than petrol or diesel cars, but they have some disadvantages. Write down one disadvantage of using a battery powered car rather than a petrol or diesel car. Well, you could have said about they've got a limited range. They can only travel so far before they need charging. But a very practical problem at the moment is that we've got very few charging points. And the other thing is it takes a long time to charge. So these batteries do not charge up quickly. So you can't just pop into a charging point, stick it, attach it to your car and be charged up within a matter of minutes. It's going to take quite a while. So that's their biggest limitation. So that's the end of the question paper, totally. So that's the third video that I've done, and I've gone through the whole mock now, and you should have a good idea of where you went wrong. Hopefully, seeing the correct answers and hearing the talk through and the walkthrough, you can see that it's not totally intimidating. There are some things that you should have got, and sometimes there's a little bit of a lack of knowledge, which comes down to preparation. And the other thing, of course, is recognizing what the exam questions are asking you. And that's why practicing papers, unfortunately, is one of the most effective ways of revising, especially when you're aiming to get up to those high grades. So continue practicing, continue getting used to the questions. You will start to spot what they are asking for quite quickly, the more familiar you become.